Okay, I want to take a look at problem 6.15. Calculation's not too bad in this one, but there are a few points to pay attention to in this equation. Basic idea in this case, in this particular problem, you want to figure out how much heat or the rate at which heat is being transferred. Now, when you see this uh, dot, basically, and when you see Q, Q is typically used to represent heat. Okay, and heat is going to be in its energy, so it's going to be in units of joules or um, for work it's the same thing as foot pounds. Newton meters, a joule is a Newton meter. So in this case, you'll see the units here. It's in meters and C degrees C. So this is in the SI unit system. But when we see this dot over the top, what that's really telling us, it's energy. In this case, it's heat energy per unit time. So energy per unit time is in units of watts, right? So we can think about like an electrical light bulb. Let's say that's in units of energy per unit time, right? Or your power that you consume, that you get from the power company's units of watts, which is joules per per second. So what this is telling us essentially is that what's the rate at which heat is being transferred? Okay. And this particular problem says you have some surrounding fluid, and you have some temperature of, in this case, it's air. The surrounding fluid is air, so we're using maybe a fan to cool it. Maybe it's like your processor on your computer. Um, and of course, this is a very large area for processor on your computer, but it's something like that, same concept here. So you blow air over the top of it, and you have a certain temperature that the air that's flowing over the top of it, and you have a temperature of that surface, right, that you're trying to maintain at 80 degrees. Okay, so they give you a so-called heat transfer coefficient, which is essentially related to how the heat is being transferred from that surface to whatever fluids are surrounding it. Or if it was if it was hotter, it would be in the other direction. It would go from the air to the fluid to the actual surface. But in this case, we're taking heat off of it, and we're transferring heat from essentially from our surface to the air. Okay. And the equation that's given is just saying, okay, that H, which is related to how quickly, heat is being transferred for a specific surface at a certain temperature, multiplied times how big it is, right? Because this term, which would be these two together, actually relates to how heat is leaving it. And then it's the difference in temperature, right? So what you would expect that, of course, that if this temperature was greater, you would actually have more heat transfer. Okay? So it'd be a desirable thing really to keep this cool if you could, if that's possible. In this case, that's the temperature that's defined. But it's really the difference between these two, right? It's going to tell you. So if the difference is larger, you're going to have more heat transfer. And that's something we're going to look at a little bit later in the chapter. Okay? Okay, just continuing on this. Now we want to go through the actual process of making the substitution. So like I said before, recognize that this is in degrees C. The temperatures they give you, here is the surface, and here is the fluid temperature, and here's the area. Notice that the units are already correct, because when we go and do the calculation, we're going to end up canceling out the meters squared and the degrees C. Okay. So it might be that you need to go through some conversions before you get there, but this problem's pretty straightforward. It's more conceptual, understanding what's kind of going on here is probably more important than the calculation's relatively simple. Of course, that's important too, but calculation's relatively simple. Okay, so governing equation we have with this problem, which was given, and all we need to do, so units are already correct, right, so we don't need to go through any conversions, is just plug the numbers in and perform the calculation. Okay? And we do that, we come up with a rate of heat transfer, which is just going to be 10.6 kilowatts, which essentially means how many joules of heat per second. Because this is just, a kilowatt is just basically a kilojoule per second. Okay, so that's the other unit that we use. And that is pretty much that problem.